Hello everybody, in this lecture we are going to start a new topic, a new chapter actually. This is chapter 8 in Rudin, and we're going to talk about integration on product spaces. So suppose you have measurable spaces X with a sigma algebra S and Y with a sigma algebra T. Then we can talk about measurable rectangles. So suppose you have a subset A cross B of the Cartesian product of X and Y. Then this subset A cross B is called measurable if A is a member of the sigma algebra S and B is a member of the sigma algebra T. And we define sigma algebra S cross T on the product space X cross Y. So X cross Y is our space, and S cross T is our new sigma algebra, and S cross T is defined to be the smallest sigma algebra that contains all measurable rectangles. Now we introduce X sections and Y sections. So suppose you have a subset E of the Cartesian product of X cross Y. Then the X section is defined to be the following: Y such that XY is an element of E. And of course, the Y section is defined in a similar way. So the Y section is those X such that XY is an element of E. So if you want to draw a picture of the X section, for example, let's say E is a rectangle, then this is our, no, that was a little bit wobbly. So this is E, this is X, pick some X, then this is the X section of this particular X. Having introduced this concept, we can now state the first theorem of this chapter, and this is the following. Suppose, so let's call this lemma. Suppose E is an element of the sigma algebra S cross T, then the X section of E is an element of T for every X, and symmetrically the Y section of E is an element of S for every Y. So proof: basically we are going to show that the lemma is true for measurable rectangles, and then we are going to use the fact that S and T are sigma algebras on X and Y respectively, and we're going to use this to show that the family of sets such that the theorem is true is a sigma algebra. And since S cross T is the smallest sigma algebra that contains the measurable rectangles, this will show that every element of S cross T fulfills the lemma. So let's start. Let's call the family of sets such that the lemma is true omega. So family of sets such that lemma is true. Suppose E is a measurable rectangle, A cross B. Then by definition of measurable rectangles, EX, which is nothing but B if X is in E, and the empty set if X is not in E. The set B is in the sigma algebra T, and the empty set is in T. So for measurable rectangles, we have shown that they are in this family of sets omega, and now in particular X cross Y is in omega. This is just a special rectangle. Now we need to show that the complement of every set E in omega is in omega. So if E is in omega, then E complement, the X section of the complement of E is the complement of the X section of E, and this complement is in T because T is a sigma algebra. So so this is fulfilled. Now we need to show that countable unions of sets in omega are in omega. So so suppose E is a union of sets EI, where each EI is in T. Then the X section of E is the union of the X sections of the subsets EI. And this union is in T because, again, T is a sigma algebra. And the second case for Y sections goes the same. So this concludes the proof of this lemma. Now we need another definition. We define monotone classes. So suppose we have a set AI is an element of M. So this monotone class we are going to define shall be called M. So AI is in M and BI is in M, and we have AI is a subset of AI plus 1 for every I, and BI contains BI plus 1. Then A, which is defined to be the union 1 to infinity over the AI, and B, which is defined to be the intersection of the BI A and B are in M. So A is an element of M and B is also an element of M. And if this is true, this M is called a monotone class. Now we need one more definition before we come to the next lemma. And this is the following. Suppose you have a set Q, which is a union of measurable rectangles, finitely many measurable rectangles. So Q is the union of rectangles Ri, where I ranges from 1 to some number small n. Then such sets Q are called elementary sets. Now, I think this is a good point to stop before we look at the next theorem in the next lecture. Thank you for watching. See you next time.